Thank you so much for joining me today. I'm really excited to talk to you about a research project I've been working on and kind of the platform that we ended up using to implement our research. So I do want to note that all of the slides, and actually the slides are the demo code, you can find at this kind of short link, which I will put in the chat right here. So you can spin this up and just in your web browser and follow along if you want. And the research that we'll be talking about here is funded actually by the Unitary Fund, which is a really neat micro-grant nonprofit that funds open source quantum development. So introductions. As Ursula said, I'm Dr. Sarah Kaiser. I do a lot of things at the moment, mostly writing books, live streaming, quantum development actually, kind of doing some community building stuff in quantum software. So if you want to see on Twitch, you can, I'm on Tuesday, Wednesdays, and Fridays at 10 a.m. Pacific. But most importantly and relevantly for our talk here today, I'm also a researcher. So I did my PhD in quantum computing at the Institute for Quantum Computing in Waterloo, Ontario, where I worked on actually building QKD hardware. So I'm by training an experimentalist, but basically kind of as I've gone through my career, I've really gotten excited and engaged with kind of the software side of things, and now actually doing full-on theory research, which kind of feels a little weird to me, but actually is really fun and exciting. So let's talk about it. So today I want to introduce you to this research project, which is basically writing a library that implements a bunch of different QRAM proposals. I want to give you kind of a tour of Q-Sharp and why we're using it for our research. I want to show you our actual literal library, some of the code, and kind of like, so you can see the Q-Sharp stuff in action. And I want to share some tools and resources. Sorry, I'm going to have a little bit of coffee here. For how you can leverage Q-Sharp in your own research and studies. And also, please, if you have any questions, please feel free to put them in chat. I'm trying to keep an eye on that. So, and I'll get to your question as soon as I can. So yeah, with that, let's dive in. A quantum memory problem. This presentation is running on RAM. In fact, actually very rainbowy RAM, kind of like the one in the GIF here. But regular RAM is really cheap, fast, and you know, you can get it and find it almost everywhere. In general, it's kind of laid out as an array of cells that you can read from and write to in any order. So, you know, this is obviously a very, very useful piece of hardware for classical computing. Do we have something, or can we think of something similar for quantum computers? So the main way that this might come in is we want to be able to transfer classical data to quantum systems. So think about, in particular, some machine learning algorithms. Often they'll just say, we assume we have a QRAM, which honestly was kind of part of how I got interested in this topic. I was talking with some of my friends who are explicitly researchers in this area, and it's like, well, that seems like a big assumption there. And so, yeah, this seemed like a really interesting question of, okay, how might we actually go about doing this? And we can see from the literature that there's a number of different kind of ways we might query some sort of QRAM implementation. We might want to query it where the kind of values we're getting out of the memory are encoded as the phase. So you can see that in things like Grover's algorithm. You might want to query and actually get like a qubit per bit value and actually kind of like be able to then just measure that whole register and read out those bit values. For algorithms like element distinctness, and as we noted before, for machine learning, quantum machine learning, like in HHL, your bit values may be actually the amplitudes of a particular state. So there's lots of different interesting ways that we can, like, you don't really have all of these options necessarily with classical RAM. There, it's just, you read out the bit values. So, our question was, and what was kind of the status of literature is it's not clear if we'll actually be able to do this efficiently at all, let alone in a fault tolerant setting. So really the trade-off that we have here is the algorithms that actually need to access the memory, they have a particular scaling for how many queries, how many times they'll need to query this memory. And a lot of times the resource estimates for those algorithms don't include the costs of querying the QRAM in the first place. So once you add those in, you can sometimes entirely wash out the speed ups that you get in the rest of the algorithm. So that's kind of, that's a little bit of a downer there. So things that contribute to why that might be costly to actually query the QRAM are potentially physical limitations. We all know that qubits that don't actually they have finite coherence times. So especially if you're trying to run a calculation, if your QRAM cannot exist for the full time of your calculation, that might be a problem. Different hardware types have different supported gates. So there's lots of different reasons why this is challenging. And there have been a ton of different proposals. And that's kind of where we're starting our search, if you will, of looking at the literature, looking at all these different approaches and trying to figure out, each one generally tries to optimize for a different resource. Like maybe one is trying to go for minimal qubit count, maybe one is trying to go for minimal T depth. And so depending on, what your actual hardware situation is, you might have kind of different trade-offs that you care more about. My goal here today is to talk more about Q-sharp and our implementation. So I will defer you to a great deep dive from one of my collaborators on this project, Dr. Olivia Di Matteo, who recently gave kind of a really good overview of what all of the trade-offs, kind of like the state of quantum RAM. So highly, highly recommend checking out this talk afterwards. And she's always on our Slack as well, if you have any questions specifically about that. So for us, so we're all sitting here, we're really interested, I'm personally interested in this question because, this seems kind of like a big loophole here. If a lot of these algorithms, if there's a potential that the speedups that they offer don't actually speed anything up if we need to use a QRAM, I would like to help figure that out. And that feels like a problem that maybe we can apply computers to, i.e. can we automate it? Can we not have to do this all by hand? So to figure out if QRAM will ever work, we need a good way to evaluate these different proposals. And when we were looking at, basically Olivia had pulled up her bibliography file and we started going through all the papers. And a lot of them are just algorithm descriptions. They don't necessarily have an implementation in any form of code. Some have some code for some of their resource estimations, but some of them, basically there's no kind of comparable basis that we can start from that all of these papers kind of provide. So what can we do? Transparency, I think, is really critical for resource estimations. We want to make sure that if we are trying to do this across the board estimation and kind of bounding of the problem, we want to make sure that our assumptions and our testing is really, really clear. And we want to make sure that other people can reproduce our results. If we have this bespoke system that can estimate the resources and nobody else can reproduce our results, they basically aren't results. So especially if we're trying to do this resource estimation, we want to make sure it's reproducible. So what we needed was a way to implement different types of QRAM, a way to count resources needed for each kind of implementation or proposal, and to do it in an open and reproducible way. So those were kind of And also my very bad Photoshop skills here. That's a particular circuit for a small QRAM. But yeah, so this is what we needed kind of after we sat down and worked out what our actual research question was. So as we kind of already, I mentioned at the top, our solution was to actually write a library in Q# that implements a bunch of different types of QRAM. So, and I will note that our project is actually still ongoing. We have a, I think, mid-project milestone check-in with our funding. We have our mid-project grant review this week, but yeah, so we aren't entirely done with all of the features necessarily that we want to have, but I'll kind of give you a sense of where we're at in a little bit here. So let's now talk about Q# and why it worked for us. So when we sat down to say, all right, if we're going to try to use computers to help us implement and do this resource counting, what should we use? There is an awful lot of solutions, which is really awesome. And one of the reasons why I'm really excited and about working on kind of quantum software development right now. So, and I would encourage, like, the Quantum Open Source Foundation here has some really good like lists, maintains some really good lists, and also has some really neat internship opportunities. So yeah, to dig in a little bit more on what we actually needed to be able to implement these QRAMs is we want to be able to implement algorithms. It's, especially as someone who doesn't come from the theory side, there was a lot of stuff kind of implicit in some of the exact details of these papers, which is why it was great to work with Olivia and Rolf and a few of the other people on the team to learn about this. But I kind of like thinking about algorithms on a higher level, like, here we're doing an address fan out, or here we're doing, and not, trying to always think about things at, it's specifically gate by gate interaction. Obviously, we also need the flexibility to adjust things at that level, at the gate level, because that's actually where we can potentially improve the QRAM. So obviously, once we implement all of these and benchmark them, then we have the opportunity to make it really easy to actually optimize the different implementations. So maybe we can apply different techniques to, and even hybridize some of them. And we also need tools that enable research and collaboration. We need ways to package our work to make it easy to share and collaborate, and especially in this case, reproduce, because we want our resource estimates to be transparent. And we want to work in a community where we're all included. That's kind of a must for me. So I have a question now for you guys. What do you know about Q#? I talked to a lot of people about it, especially after we've been working on this project, and please put in chat, if you're able, any and everything that you might know about Q#. I will, nothing. That's fair. You are not expected to know anything per se. The empty set. Yeah, this is a Visual Studio's a pain. What you told me. That's fair. Well, that's awesome then. So I'm excited to be able to share with folks what it actually is, because for whatever reasons, it seems like it doesn't, the media campaigns are maybe not the same between the different tools. And we went through and we're looking at kind of the technical aspects. You can program quantum algorithms in Q#. Yes. No, that's okay. That is a very important point. Thanks. Cool. So let's kind of actually try to define what this is. So Q# is Microsoft's quantum programming language. It is so I put new here to emphasize that it is not C#. It is not a derivative of any other language. It's an entirely new language. It's open source. That's domain specific for quantum computing. It's not based on F#. It is an entirely new language. where you might see things like F# and C# involved is on like in the back end where they're implementing the compiler for Q#. Like the compiler for Q# has to be written in something. And so like some of the back end tooling is implemented with those things. But when you write Q#, it is not based on F#, it's not based on C#. You'll see some flavors of different languages kind of in the design. Honestly, mostly Python from my experience, but yeah, it's an entirely new language. I thought Microsoft used to have a Sharp-based quantum info language. Is this built on it? So they had something called Liquid. That definitely had some F# stuff. That would be relevant to like the simulator that's used here, but the language, it's entirely new, everything like built from scratch. Because one of the design principles actually for it is to be a quantum first, familiar second. That was from like one of the developer blogs that I was reading. The idea is that this, quantum computing is like an accelerator hardware or accelerator platform, right? You use it to accelerate certain types of computations. So you kind of need a language specifically designed for that hardware to best express its capabilities. So you see this all the time with like GPUs that have, their own languages like CUDA, and then you have tools that generate, take code from say Python that translate it to CUDA. So you can, the quantum development kit is basically all the tooling around Q# that you need to kind of do to write your code. So it's like editor extensions, it's the compiler, it's the runtime, it's libraries. So the development kit is kind of like all of the infrastructure that goes with the language. And honestly, that's kind of one of the things that at least I personally was most excited about Q#, was because I use for Python and for everything else, I usually use Visual Studio Code as an open source editor, and the integration with that was really, really nice. And yeah, and Q# is also designed to be integrated with a number of other languages and platforms like Python and .NET. So what that means, kind of like I was just saying, given that quantum computing is likely going to be like a hardware accelerator, you can run your Q# as kind of like a subroutine for a program in Python or in any other .NET language. And honestly, it wouldn't be too hard to potentially add other hosts. So yeah, that's the main idea. Q# is an entirely new programming language, not related to necessarily C# or any of the other languages. That's specifically intended to be designed to describe what quantum hardware can do. So to kind of give you an idea of what, this isn't exactly a stack, but kind of the relationship of the parts here. So on the left, we have, you'd have like your Q# program. Your Q# program is going to contain operations and functions that you write. You're going to be able to include and leverage libraries, which honestly is a thing that, at least for QRAM, made our lives a lot easier because there was a lot of stuff already implemented we could just leverage. So those things together kind of constitute your Q# program. Then, as we were kind of talking about, you would basically have a host program run your Q# program for you. This is now actually of a couple recent updates ago, not strictly necessary. You can compile Q# to be like an executable that you just run at the command line. So you don't even have to write an explicit host program if you don't want to. But then the idea is that your program can be run on any number of different target machines. So the idea is kind of write your quantum program once, and you can run it against a simulator. You can run it against a resource estimator, which might be one of the other things that sounds like it could be useful for QRAM, and you'd be right. So Azure Quantum is going to be the like hardware target machine option as that comes available. My last understanding of that is later this year. I think that was the announcement at Build earlier this year, but they are in a private preview for this. So basically, in the same ways that you could just take your program and run it on the simulator, you can just point it to a different target machine, and then you're running on hardware. Yeah, so let's actually let's take a look at some Hello World stuff. So since everyone always starts with Hello World, here I have written a function. You might notice that this kind of looks like a Jupyter notebook in the presentation. You'd be right. So I'm actually running Q# code right now with a Jupyter kernel for Q#. So I can define functions and operations in here. I can use libraries in here, and I can actually simulate and run my programs. So in this first cell here, I defined a function called greeting. And here it takes an input name that is of type string, and the return type is unit, so it doesn't return anything. I'm also just going to very briefly want to restart the kernel here, just because it looks like I lost my syntax highlighting, which is a bug in my in what I have done to my machine here. Restore it. Yeah, okay, there we go. I like my syntax highlighting. Great. Okay, so we'll run that again. Awesome. So that's our Hello World. Functions are basically a great way to define deterministic classical calculations. So, you know, kind of think of them as like mostly being what you could describe as an actual mathematical function. And another thing to point out here is that Q# is a strongly typed language. So you will see types everywhere because they are necessary. So let's look at another function here. So I'm going to actually start by opening a library here. In this case, it's the math library, which has definitions for the type complex. So there are a bunch of built-in types for Q#, but you can also define your own. So here I'm actually going to show defining a new type. So you can see this new type keyword here. Like, this is entirely arbitrary. I was just trying to kind of like make up a reasonable example here. But I'm making a new type that contains a complex array. It has two named items here. One that is the count. So that's basically like how many items are in the array. And another that is the value. And that's going to be comprised of complex typed things, and the square brackets here mean an array of. So the values here are going to be the actual array of complex numbers, and then we also have this named item for count. So let me actually remember to run this. All right, good. So let's define a function to actually use this. We can define a function that, you know, does some classical data processing here. So it's going to take in some data that's actually an array of doubles and turn it into an array of complex numbers. So these would be all real numbers, but now they're of the right type. So they actually be of type complex. So this returns then a complex array. We go through and define basically a mutable result where we're going to be stashing our actual converted data. You can see by the fact that we're defining something to be mutable here that that might imply that the default is everything else is immutable. You'd be right. So sorry about that. We have, you know, control flow and control loops here, just like you might expect from any other language. So we're going to say for every item in our data. This to me feels fairly Pythonic, actually. You have just an iterable that you can just say for every item in it. And then we're going to update, we're going to set things in our results. So basically what we're going to return, and we're going to set the values property here with basically what we had before and a new, basically the new item that we're converting to a complex type. Don't worry too much about so here the syntax with the double colons means we're asking for the list of values from the results type. And here the with/equals is basically like set, like update the value in place. So we're basically updating the value of values here with this value. I realize that's kind of a mouthful. And then at the end here, we return our results, and we just make sure to set the count property here with the actual length of our values. Great. So again, this is a not a terribly well motivated sample, but we're just trying to do some data conversion that you might need to do for something. So I've also defined one more function down here, which just makes this easier. So I've hard coded some data here, being just like the doubles 1, 2, and 3, and then returned as complex arrays. So now that we've defined all of that, does Q# have higher order functions such as map, filter, and fold? Yes, it does. Absolutely. So there are a lot of, and I love using those. You do not have to do everything kind of with for loops, or there's a lot of functional flavors to this. Absolutely. So here we can simulate it, and you can see it returns our complex array that's of length 3 and has the values here, complex values now of 1, 2, and 3. Great. Generally speaking, you probably don't just want to do classical data processing with a quantum programming language. So let's talk about actually using qubits here. So qubits are a resource that can be requested from the runtime when you need them, and you return them when you're done. So they're not, so we basically need to ask the runtime for them, which I think matches pretty well with like the model of you have hardware device that has qubits, like you don't get to own them, the device has them, and you're just sending instructions at it and hoping it does what you want. So previously we've defined a bunch of functions. Now we actually, the other thing we can define and really write in our code is operations. So technically operations cover anything else you might want to do that can't be written as a function. I generally tend to think of them as basically, if I want to work with qubits, I definitely need an operation because these actions, the action of your operation on the qubits is viewed as a side effect here. So let's just define an operation. We're going to make a simple QRNG. Doesn't take any arguments because it doesn't need any. And it's going to return a type result. So to request said qubits from the runtime, you use a statement called using. And using takes an argument that basically is the name, like what you want to call the qubits, and then effectively like the number of qubits that you want to request. We'll see some examples here in a minute of requesting multiple registers full at once. That's totally fine. Here we're just requesting a single qubit. Then as you might guess, and as many other platforms and languages have, there's tons of built-in operations. H is a Hadamard operation. So that basically puts our qubit in superposition. And then we're going to return M reset Z. So this is actually something that comes from this library that I forgot to mention up here. The measurement library gives you all kinds of different options for like measure as an integer. So like you don't have to do all of the manual, like, all right, here's a bit string. Is it little endian, big endian? Like, there's lots of great utilities for measurement in this library. So this one takes your qubit, measures it in the Z axis, and then resets it. So as a part of when you request a qubit from Q#, you are guaranteed that it's coming, like you get it as a 0 state. You do also have the possibility, there's also a borrow operation as well. So if you don't necessarily need a fresh qubit and you just want to kind of borrow one from somewhere else, you can also do that. But generally speaking, you want to request a fresh qubit. So that's where you use the using statements. And then as a part of that, the scope for basically how long you'll have the qubit is these curly braces here. So this kind of defines the scope over which you have borrowed, or that you have requested those qubits for. So when we get to the end of it, we need to put them back in the 0 state, so that when they go back to, when they're released, kind of we've met the same promise that the runtime has. So that's why there needs to be a reset here. And there are some situations where the compiler will actually know how to reset it for you, so you don't have to actually, so like say if you've already just measured the qubit, technically they've added this recently to the compiler that the compiler can figure it out and you don't have to, or rather the runtime will figure it out and you don't have to. But generally speaking, it's kind of good practice to clean up after yourself, because after all, most quantum operations, all quantum operations except measurement, should be reversible. So let's run this. Great. And let's actually simulate it. So we can run this a bunch of times. We should get, roughly 1 and 0. Yeah, this is exactly what you would expect from measuring kind of a equal superposition. And again, please, if you have any questions about this, please feel free. So you can run all of this in your browser with the link I posted earlier in the chat. And yeah, if you have any questions, please put them in chat. So this is good, but we're going to need to write some more operations that aren't kind of as trivial. So one of the really cool things that I learned about Q#, which it viewed that as part of the markdown header. What? Weird. Anyway. Nope. Okay. That's Q#. Sometimes you'll often see it written out like this, just because the sharp symbols sometimes are not a good thing to search for or get excluded, as in like regex searches. Anyway, so functors are a really interesting thing in Q#, which basically, so there's a couple functors, adjoint and controlled, which basically allow you to take an operation, and without you having to implement any additional code, it will give you the opportunity to use either the adjoint, or basically the conjugate transpose of that operation. It'll calculate what that is for you, or the controlled version of that gate. So there's pretty well-known kind of like ways to do both of those things, but basically the compiler will take care of that for you. So for example here, I'm going to define an operation that's just simply apply an x to a qubit. So that's a poly x operator. So that's going to flip it from 0 to 1. You can see here I'm not like allocating any qubits in this operation, and instead take a qubit as an argument. So this is, you could think of this operation as being purely just the matrix that represents the poly operation. And then the second one I have defined here is apply a multi-controlled knot. So now we've added one more input here, which is a control register of qubits. And all I have to do is take the operation that I had before, apply x, and put controlled out front. And that basically what that does is, you can see now we have an additional argument to apply x that's added right at the beginning. And that can actually, we can specify an array of controls that will control the application of whatever we've put here, which in this case is apply x. So come on, let's go to the next one. Great, so let's actually use that then. Again, I'm making use here of yet another library called diagnostics. And the operation here where I'm actually going to test this, or show you how it works, is here. So we're going to use control functor. Don't take any arguments and doesn't return anything. So we're going to use our using statement here to allocate some qubits. And here we're actually going to name two registers, controls and a target. And you can see here that our controls, I've just decided and hard-coded that there are 2 control qubits and 1 target qubit. Okay, so once we're now in the scope where we have the qubits, I'm going to apply a Hadamard to both of the controls. So this is kind of like starts to get towards those map and filter functions. There are things that are directly those. And then there's also ones, a lot of them that are kind of like nice specializations of some of those functional ideas that are common things you see in algorithms. We've now put our control register in a uniform superposition. Then we're going to apply our multi-controlled NOT. And then to actually see that it did what we wanted, we're going to dump all of the information that the target machine has about our calculation. So it is important to note here that it is whatever the target machine knows about it. So since I'm running on the simulator, this will be everything, the full state of the registers. If this is running on hardware, dump machine would give you something very different because, well, we can't just ask a literal physical qubit to tell us the vector that represents itself. So it would give you things potentially like, you know, hardware temperatures or different signal statuses, stuff like that. But dump machine is a really helpful kind of like, just tell me what's going on sort of debugging tool. And then at the end here, we're just going to reset our registers. Kind of as I mentioned before, we're promising to give them back in the 0 state here. So let's make sure I actually ran that. Okay, good. So now that we've actually kind of written a program here, I get it's very minimal, but where can we actually run Q-sharp programs? I mentioned we can run them from the command line as standalone applications. And honestly, that's where we do a lot of our testing in our library is like, we've written something real quick and we'll just run it from the command line, you know, maybe with an argument or two. You can even do that. We can also run them from Python or .NET host programs. So you can, from your Python code directly, just ask Q-sharp to run a particular operation. And that's actually what Olivia has been doing a lot of, because it's very easy for her in Python, and is also easier for me to do a bunch of you know, classical data processing, you know, maybe randomize the contents of a bunch of QRAMs. Then we can pipe that into Q-sharp, and then after we get the data back from Q-sharp, we can use Python to do some really easy plotting and stuff. So we're hoping to get that kind of, that pipeline really, really nailed down so that it's just super, super easy to just kind of swap out to new QRAM implementations. And you can also, as we're doing right here, run in Jupyter Notebooks with either a Q-sharp or a Python kernel. So when we run our use control functor, what you see output here is the contents of dump machine. So this basically gives us, we can see here we've got 3 qubits, and it gives us basically a full listing of all the basis states and the amplitudes of those states. So I think this did what we wanted. So we can see that it's an equal superposition between 0, 0, 0, 0, 1, 0, 1, 0, 0, and 1, 1, 1. So that's basically, the first 2 qubits were our controls. So those are, we're picking out each of those combinations. And then the 3rd qubit should basically be only flipped in the last case here. So I think that did what we were expecting. But this is a really helpful tool, and there's some really neat, I've been helping test some really neat like inline debuggers here where you can actually step into and out of your program and see like the amplitudes as you go. So kind of along those lines, there's more here than just, you know, you've mostly seen me use %simulate to actually run our code. There are a lot of different, these are technically called magic commands in Jupyter. This is more than just a Q-sharp concept. This is a Jupyter and Python concept. But these magic commands, you can use ls magic here to just list all of the ones that are supported currently by the Q-sharp kernel. So you can see other things here. You can see simulate, you can see estimate, which we'll take a look at in a second. You can load arbitrary other packages. And you can actually see here, they've already started putting in the plumbing for the sending jobs to hardware. So, you know, once the rest of that's in place and you have access to the device, you'll be able to submit your jobs directly from here, which I'm really excited about, but have not done yet. So yeah, let's actually just try this. So we're using the percent estimate target machine. So this is basically corresponds to the resource estimator target machine. And it will just straight up tell us what resources it would take to run our operation here. Now, I'll note that estimate here doesn't actually run the calculation. So what that allows you to do is actually estimate things that are much larger than you can actually run. So at least the built-in simulators for Q#, you can run on a decentish computer, I think up to like 30 or 32 qubits, something like that. I think with my egregious amounts of RAM, I can get up to like 34, maybe. But yeah, basically, obviously there's an exponential overhead as you go there. So yeah, like that still is though quite a few qubits that we actually leverage a lot to do some testing. So as a segue to what we're going to talk about next, which is how do you actually, say we've written, okay, so we have these QRAMs, QRAM algorithms, we've written them in Q#. How do we actually know that they match what the paper said? That's always the, you think that's the last 20% that takes 90% of the time. So there's a lot of helpful kind of operations and functions in Q#, particularly in different libraries. Again, so you can see here we're actually using the array library. But we can do things like use facts to check basically classical data. So here we have an int that we're saying is the number of qubits. We can assert that this is a fact. So Python has some pretty similar kind of, I can't remember if it's also called fact or not, but the idea is that these can be safely stripped out at runtime, but compilers will, or can't quite remember. But basically, these are things that you can assert about either classical inputs. So that's one way. You can also use asserts on qubits. So if you know that, say, the paper had worked through an example and you had the state that a qubit should be in after a particular operation, you can use assert qubit to say, hey, I think, this qubit should be when we measure it in the 0 state. So in this case here, we're actually just straight up checking to make sure that when the compiler is giving us, or when the runtime is giving us a qubit, that it's in the 0 state. So here, again, here's our using statement. We're getting a register of qubits of length num qubits. And then for each qubit in that array, we're going to basically check that it's in the 0. It measures in the Z basis to 0. There are a ton of different, like, as I noted before, like kind of specializations of this. You can assert with a tolerance. You can assert with different measurement bases. You can, there's lots of different options here. I picked kind of one of the most simple ones in this case for this particular test. So, but we can run that. And then we can simulate that. And in an ideal case, if our tests pass, nothing happens. I did add this additional message that says test pass just to make sure it did something. But yeah, so in an ideal case, you then just have all your tests pass, and hopefully you can add enough tests to be confident that what you've implemented matches your paper. So there's one other kind of really helpful, I thought this was just really cool, sort of testing concept, I guess. You may also want to test that an operation that you've implemented does what you want it to do. And this is especially important to us because we're going to be doing a lot of like, here's a QRAM and here's like an optimized QRAM. Does it still do the same thing for all inputs? Like that's what we want to test. So that's fairly important to us. And we could obviously manually test all the inputs, or we could try some select subset of states where we're pretty confident if all of those work out, the rest will. But something that I learned from reading in the docs, Q# uses the Choi-Jamlikowski isomorphism to make an assertion about operator equivalence into one about preparing states. So the basic idea is if you have an operation and you have another operation you think is the same, ideally, if you did one operation and then did the adjoint of the other, that should be an identity channel. Like that should not do anything if they were truly identical. So Q# has an operation called assert operator equals referenced. And basically it will create what should be an identity channel with the two operations you're proposing and apply that to 1/2 of a maximally entangled state. And basically then you can assert that it is still the maximally entangled state at the end. And if that is true, because this is an isomorphism, you are guaranteed that those are actually identical operations for all inputs. So let me show you an example of that. Here, again, we're going to be using diagnostics, but importantly, we're going to make an operation here that just applies C0 to a register. So it's going to take the first qubit and the register as the control. In general, Q# controls are listed first, and then targets or anything else is listed after. You could see here we could have actually also used the functors, but there's actually also a built-in C0. And we're going to make the second qubit the target. All right, so remember that. So now we're going to define C0 the other way, which is, you can see here, the C0, we're actually making the target the second qubit, and the control, sorry, let me say that again. We're going to make the control on this C0 the second qubit, and the target the first qubit. Now, it's a well-known circuit identity that if you apply H on each side of your C0, then, so like on both qubits and on both sides of the C0, that will actually flip the direction of your C0. And so you can also see here another neat pattern in Q# that I use all the time, which is within apply. So the idea is that it runs the operations in the within block, then runs the operations in the apply block, and then goes back and runs the adjoint of everything in the within block in reverse order. So it's basically like prepare your state, do what you want, and then undo your preparation. So this is just such a helpful thing because I very frequently forget to do the right adjoint or do them in the reverse order or whatever. Like it keeps you, it saved me from making a lot of mistakes, let's just say. So that's a great pattern I leverage all the time. Okay, so now we have these two implementations of what we think should basically be the same C0 gate. How do we check that they actually are? So here we're using assert operations equal referenced. And the first argument here is just the number of qubits we need to test this. And then here's our apply C0 operation, and here's our apply C0 the other way. We can run that, define it, and check that it works. So that basically guarantees us that those two operations for all inputs, all possible inputs, are identical. So yeah, I thought that was a really clever way to leverage the channel state equivalence or Choi-Jamlikowski isomorphism to do some neat testing. Yeah, so to kind of summarize what our plan here is, is we want to use functions and operations to implement our different QRAM proposals. We want to leverage the libraries and functors and other things like within and apply to reduce how much code we need to write, which hopefully should also reduce the number of bugs we can possibly introduce. We want to use some of these testing features to make sure what we actually are writing does match the papers, and then profit, but more importantly, as academics publish. So yeah, that's kind of how we saw using these Q# features to actually do what we needed here for our project. So now let's actually get into some details about the project. I'm gonna just, in case people want to take a look at the repo, put that in chat. So The basic layout is we have kind of 4 main root directories. We have our source, which is where all the actual QRAM is implemented. We have our tests, we have samples, and then we have docs. So pretty straightforward. So looking at the source, basically this is what my computer looks like most of the time. I have like some tech and the paper that either we're writing or someone else's paper that I'm trying to check against. And then I have our Q# up on the other side, where I'm actually trying to like compare or implement or whatnot. So here, this is a screenshot of using Q# with Visual Studio Code. You can, use whatever editors you'd like. There are currently, the best support is for Visual Studio Code and Visual Studio. Honestly, Visual Studio scares me so much, so I never touch it. But you have parity with the features between the two, and so I can use the tools that I'm familiar with, as well as most of the rest of my team. They were all using either Visual Studio Code or Sublime or similar. So currently we have implemented the most common QRAM proposal, which is Bucket Brigade. And then we have a couple different QROM proposals. So the difference between these two is basically QRAM have specifically allocated registers that are the actual memory. So you have to kind of keep track of that. QROMs are basically like read-only, so they're read-only memory, and they're basically like hard-coded lookup tables. And you can actually do that by just specifically ahead of time designing a circuit that you just pass it an address and where you want the data, a register where you want the data to go, and a query is just kind of running that one operation on it. So as long as you don't need to change the values of your data, the QROMs can be potentially a lot less costly, especially in terms of qubits. So these are the archive identifiers for the paper. So if you want to check any of those out, here's an example of like a custom type that we defined for our library here. So you can see we have, this is our QRAM type. Oops, I didn't mean to do that. We have 3 named items here for basically a phase query, a bit query. So these both define operations on our QRAM. The write is also an operation on our QRAM, but you can see, and these are the type signatures for those operations. So a query here takes as input, an address register, a memory register, and a qubit array, which is basically where the target. And similarly here, and then for a write, you just need a memory register and a memory cell. And a lot of these are all custom types that we've kind of added as a part of our library to make our lives easier. Our QRAM type also has a couple metadata named items here as well, just to make it easier if you need to check later, like, oh, I forgot what the data size for this memory was, to know how many qubits you need to allocate. So let's actually load it up and use it. So we can use the package command here to load our library. We can use a bunch of built-in libraries also to bootstrap, but you can see the last one here is us actually opening the namespace for our library. So I'm just going to define, here we've got some classical data processing. We're just hard coding some memory data. And here's basically the meat of using what it would look like to use a QRAM here. So here's our using statement. We've got our qubits. We're going to prepare our register, basically apply poly from bit string, takes a bit string, represents our address, and basically applies poly x's where we need to turn that into basically a register that represents our address that we're querying. And so here's our memory, and the double colon asks for the named item of this type, read, and that's it. It's really pretty simple. So this will basically query a particular take a QROM, query at a particular address, and then measure our results as an integer. So basically, it'll be human readable to understand the output of this. So I need to make another operation that actually includes defining the data and creating the memory. So yeah, that's our example memory data. We're going to declare a memory like this, and then we're just going to return that result. I'm going to go a little bit quickly here. So there we can simulate our, literally simulate our QRAM. So given we're querying at address 2, we would expect to see 5. Okay, that's good, that checks out. And here we can literally just run estimate, and we can see that, you know, it took 7 qubits to do this. It had a T depth of 70. Total number of T gates was 105, took 6 measurements. So yeah, like we have everything here that we need to actually kind of start compiling this for our research. We also have a bunch of unit tests written that basically test our QRAMs for small instances, which, you know, we go up to basically as large as we can reasonably simulate. But then we can also run tests on larger instances by checking to make sure they have the right number of resources that we expect to see there. We also have the docs folder there is to really help us help others use our work as well. So you'll find a great primer on QRAM that Olivia has been putting together in our repo. And what's next is we want to break down our resource counting kind of into different subroutines of our actual quantum programs. So the resource estimator here is kind of actually a special case of a more general target machine that QSharp has called the trace simulator. So there we can actually really kind of fine tune and customize like what gates do we even want to count, you know, and where and how we want to be counting things. And in particular, we want to make sure we're counting separately for like how much a query takes, since that is going to be the main thing that fights our scaling when we're trying to actually understand if these QRAMs are feasible. We want to do other things to make this more accessible for folks, which is adding more documentation, making sure we will have a research paper compiling our results, and hopefully add some more QRAM and QROM proposals in the future. Thanks, Eric. Sorry for running a bit over.
Just a reminder about the time, just in case there are people waiting in the other meeting. Thanks.
Yeah. I just want to put up a couple of resources here that, so if you want to get into using some QSharp for your research, I would suggest taking a look at the docs, which is docs.microsoft.com/quantum. I've written a book actually that kind of introduces QSharp with Python. I also do live development on Twitch, so I write QSharp live and let everybody on the internet critique me. And also importantly, check out QSharp community, which is a really great community group where I'm a maintainer for, but basically is a really great place that I found a lot of team members and collaborators, and we're making some really great projects. So yeah, QRAM is one of them. So I will leave up some links here, and thank you so much for your time. Is there any other questions? And please feel free to, yeah, go ahead, Serene.
Hi, can you hear me?
Yep, I got you.
Okay, that was a sweet talk. Thank you very much. I have a lot of friends who do physics, and I'm a PhD in computer science, so I've been asking them about quantum computing for years, and nobody's been able to give me a good explanation. Thank you. But I do research into interactive theorem proving and particularly formalization of mathematics. And I've seen a lot of people do programming language verification with languages like C, so that we can prove that C programs terminate in the ways that we want them to, or whatever. And I was just wondering if there's anything going on within quantum languages here, because obviously the facts about the programs you are writing in Q# are actually relying on quite complex mathematical facts in linear algebra and with Hilbert spaces and stuff like that. And I noticed that that Q# uses this isomorphism to basically proved property of the equality of these two functions using this isomorphism. So I was just wondering if there's any talk of this kind of thing within your field and perhaps where I can look.
Yeah, so I think the term for this, and my disclaimer is I'm not, I'm an experimentalist by training, but I think that's called like computability questions. And definitely there is research going on about that. Honestly, drop a question in the Q# community Slack. I know, like, I'm pretty sure Chris Grenade maybe has not worked on it, but would definitely know some good papers to point you towards.
Yeah.
That would be a good reference.
Cool, thank you very much.
Mm-hmm.
Okay, any more questions? Just as a reminder, we have now a private meeting with Sarah, with the International Graduate School of Quantum Technology students. So if there are no more questions, I invite the students and Sarah to go to the other room now.
Sounds
Thank you,
good.
Sarah. Okay.
Thanks.
Good. See you now.
Thanks, everybody. Yeah.